Hello, my name is Lauri Nyrhilä, and this is my master's thesis public presentation. The thesis is about benefits of increasing flexibility in a low temperature district heating and cooling area network case Aalto Works District. This thesis is conducted as an assignment to Fortum, and the presentation is recorded in February 2021. Okay, let's begin. Okay, let's look at the structure of the presentation. First, we have a short introduction on the study itself. Then we're gonna take a look of the background of the research and the subject itself. Then we'll have a description of the case, the AltoWorks network and its solutions. Then we'll look at the model and its components and how the modeling itself was done. Fifth, we're looking at the results of the different scenarios that we have modeled. And finally, we'll analyze the results and have a short discussion. So, AltoWorks District is a pilot project by Fortum. It consists of a low temperature district heating and district cooling area networks. The heating and cooling is provided by dual source heat pumps, and the purpose is to provide CO2-free heat and cooling production, and as well as act as a pilot project for this type of solutions. We're introducing flexibility to the network in different ways and volumes. We're measuring the benefits by increase in self-sufficiency and in heat pump capacity utilization, as well as in resulted monetary value creation. We're creating the model of the AltoWorks district inside an existing Espoo district heating network model and modeling it with a tool called Mona. We're looking at 4 different scenarios, which we are then optimizing and running in the Mona model. And our focus is on the network in a system level, meaning that we're not particularly interested in single components, whereas the network as a whole. So a bit of the background of the subject. Heating is responsible for 30% of domestic greenhouse gas emissions in Finland. It goes without saying that decreasing greenhouse gas emissions is a global effort, and Finland has set very ambitious goals as well. Heating market being a major actor has to also adapt to be able to reach the goals. Also, an increase in building energy efficiency means that the consumers will require less heating, and that itself results in a relative increase in network losses. These issues can be tackled by lowering the supply temperature of the district heating network. That will decrease the network losses as well as make it possible to efficiently utilize low-grade heat sources such as waste heat from industries and data centers, as well as renewable energy sources such as ground source heat and heat from the ambient air. It's also possible to utilize plastic piping in low temperature district heating networks. It is fairly new solution to use plastic piping, and in Finland there's not much experience on the subject. Anyways, the transition to low temperature district heating is well, slow and has not been taken place yet. The district heating is a investment heavy industry. There are lots of existing currently operational investments that still produce profit for the district heat network operator, as well as so it's making the transition less desirable, as well as LTDH produces a reduced system design margin. This means that the district heating network usually operated with a large margin, a safety margin, so a higher supply temperature and and backed up with abundant amount of capacity to ensure the security of supply. With the LTDH, this is not possible, and it's kind of counterproductive towards LTDH. Therefore, we need for LTDH to be a success, we need a very more in-depth optimization and better modeling on the networks. There are small-scale LTDH pilots and adaptations in the world. For example, there are networks in Denmark, United Kingdom, Sweden, as well as in Finland. So, about the case itself. So the Aalto district is in Espoo Otaniemi, and it's inside the district heating network of Espoo. The purpose is to provide space heating for 5 existing consumption points in phase 2. In phase 2, there will be new buildings that will not be connected in the Espoo district heating network, but we're focused in phase 1. Cooling is provided for a helium production unit and 2 other buildings in the network. So the heat and the cooling is provided with 2 dual source heat pump units. If the heat pump units fail to provide enough heat, for example, if the ambient air is too cold, it's possible to utilize heat from Espoo district heating network because of the existing network connection in the buildings. The temperatures of the network is 45 and 30 Celsius in the heating side, and the cooling network is 10 and 16 respectively. We're looking at the increase or introducing flexibility by first looking at the network flexibility, so using the network as flexibility itself, heating up the network over the 45 temperatures and then cooling it down. Secondly, we're looking at the possibility to pump heat from the low temperature district heating network to Espoo district heating network with a heat pump. And thirdly, we're looking at a heat storage unit, which is actually an existing oil container in the area of Otaniemi, which could be retrofitted as a heat storage. So about Mona and the model itself. So the Mona is an optimization tool created in-house in Fortum, and it's a mixed integer linear programming tool. It has a graphical user interface, and it requires actually no text-based programming for the user to create models. The model takes inputs from outside, such as production temperature, electricity, and fuel price forecasts, and the model minimizes the production costs of the heat. So the AltoWorks model is optimized as a part of the Espoo district heating model. So the model tries to minimize the overall costs and not only the costs of the AltoWorks district. The components in the model are the heat demand and cooling demand, heat production units, so the heat from the cooling network and heat from the air source, and then the 3 flexibility options discussed before. And the scenarios that are simulated and optimized are of course, the base scenario without any flexibility, and then with the 3 flexibility options individually, and finally with the all-on scenario where all of the 3 flexibility options are included. And the optimization is done in a 1-month period, March 2020. This is because it takes a very long time to run the model. It requires a lot of processing power. So when wanting to run multiple scenarios, it's not feasible to do for example, a whole year. So we decided to run a 1 month in actually two periods or in 2 weeks. And We chose March 2020 because there's a large variance in both electricity price and temperature, which can be seen in the figure. So the heat demand was modeled based on existing consumption data from the consumption points. Since the buildings are existing customers of Fortum, we have existing hourly data on the demand of heat for each building. So they were just sum up together and then matched with data on the outside temperature from each time. Then a simple linear regression line was created and creating a heat demand function. The cooling demand was a bit trickier. There is no existing cooling data on the building other than that the helium production unit requires a constant cooling. The designer of the network, Sweco, created a cooling demand duration curve, which then was matched with historical temperature data from the last 5 years. And then with that, a piecewise function was created for the cooling demand. And here is the entire Aalto district system modeled in Mona. First, on the left, we have the heat pump production. There is the cooling production unit, which is modeled here. Here we get the cooling demand based on outside temperature. Here is modeled the maximum capacity of the heat pump, the maximum capacity of heating the heat pump can provide. And finally, here is the decision variable of the heat pump unit, how much heat it will actually produce. The model will then match it with the demand right here. Demand is calculated here based on ambient temperature. And then the model has to decide whether it will use the production from the heat pump units to answer the demand, or if it will choose to use the heat from the district heating network. It can also store heat produced in the heat pump units inside the oil tank unit or the network flexibility. It is also possible for the model to pump the heat to the Espoo district heating network. Okay, and all of these have certain costs, and they are introduced here to the continuous costs variable. Okay, so results. First, we have the base scenario where no flexibility was introduced. We were able to achieve self-sufficiency of 89.1%. In the agreement with the customer, there is a requirement of at least 70% of self-sufficiency, so this fulfills it easily. The capacity of the heat pump units was utilized at 89.5%, which can be seen from the right top hand corner. We see that there is almost always there is at least some capacity available to be utilized. We also see from the left bottom corner that the indicative costs of the heat pump production is significantly lower than is the production cost of the Espoo district heating network. So this suggests itself that there is a possibility to increase increase monetary value in providing flexibility. Next, here we have results from the network flexibility scenario. The network flexibility provided a kind of a heat storage of 336 kilowatt hours by increasing the supply temperature of the network. No cost to the increase in supply temperature was introduced, even though it has to be mentioned that in reality the coefficient of performance of the heat pump units would suffer from the increased temperature or the supply temperature, and of course there would be a slight increase in network heat losses as well. But it was decided that we wanted to first take a look of the possible value created with this solution before modeling it further. As we can see, the capacity was rapidly utilized. This is the shows on the daily level or the monthly utilization of the capacity. So it was rapidly charged and discharged. As we can see in the curve, the self-sufficiency was increased only by 0.8%, as well as the heat pump capacity utilization. And the heat costs were brought down by 0.68 euros per produced megawatt hour of heat. Okay. Next, we have the heat storage scenario. In this scenario, the oil container was modeled as a heat storage unit with 26 megawatt hours of heat storage capacity, and no costs to storing or discharging heat from the storage units was introduced. And as we can see in the bottom left corner, the heat storage was actually not fully utilized in the model. It was only utilizing around a maximum of 20 megawatt hours of the heat, and that only a short amount of time. The self-sufficiency of the network, as well as the capacity utilization of the heat pump unit, was brought up to 6.8%, bringing down the heat costs by 2.18 euros per megawatt hour, which is actually a significant decrease in the production costs. By introducing the heat pump to make it possible to utilize the heat in the district heating network, in the Espoo district heating network, the self-sufficiency and the heat pump capacity were actually increased more than in the heat storage scenario. There was a cost in utilizing the heat pump. It had a coefficient of performance of 3.3, and the costs included electricity, transmission, and tax costs, of course, without value-added tax. Whereas the self-sufficiency and the capacity utilization increased by almost 7%, the heat costs were actually brought down only by 0.44 euros per megawatt hour, which is less when compared to the heat storage scenario. And finally, in the all-on scenario, we had the both network flexibility and heat storage, and as well as the heat pump to the district heating network. The self-sufficiency and heat pump capacity utilization were increased notably, both by 11.8%, and the capacity of the heat pump was actually utilized 100% of the time. As we can see on the top left corner from the heat production curve, we see actually that the model used district heating to provide the heat to all the network to be able to store the entire production of the of the heat pump units into the heat storage, whereas the heat pumps, the DH network, were actually not utilized that much. And the heat cost was brought down by 2.43 euros per megawatt hour, which is an increase compared to the other scenarios. So, first of all, based on the results, the network flexibility does not seem to increase value creation. As discussed before, no costs were introduced to increasing the supply temperature, whereas in reality it would include some costs, and most likely the costs would mitigate the increased benefit, at least monetarily. The heat pump to the district heating network provides increased value, but it requires large investments compared to the heat storage. A heat pump unit is usually an expensive investment, and at this model and in this solution in the AltoWorks network, it doesn't seem to be a beneficial solution. Whereas the heat storage provided basically infinite flexibility for the model, since the storage was not fully utilized at any time. And we chose this scenario to be subject for a bit further analysis. Finally, we'll note that the all-on scenario with all the possibilities included had more value created, but when compared to the heat storage scenario, did not increase the value significantly. So, analyzing a bit on the heat storage capacity, we see that from a sensitivity analysis, that the decreased production costs increase by a large amount, from around 1 to 4 megawatt hours of storage capacity. So based on this figure, we can deduce that the optimal heat storage for this model is around 3.4 megawatt hours. So if we estimate the investment cost for heat storage to be around 7,500 euros per megawatt hour, the return of investment would be around 30 similar months of operation if 4 megawatts hours of storage was chosen. So the study can conclusively say that there is increase in value creation provided by introducing flexibility in a area district heating and cooling network. The actual monetary value cannot be concluded, and the study recommends that a further research by simulating heat storage with 12 months time frame would be recommended. It also should be considered if there is a possibility to utilize a large capacity of heat storage as a seasonal storage, whereas in this was only utilized in just a couple of weeks time frame. It should also be considered that if there is an abundance of cooling heat or heat produced from cooling, would it make beneficial to install a heat pump from a similar type of low temperature district heating network to pump heat up to the district heating network, and how much heat should there be, or how much free cooling heat should there be? This study acts as a good basis for a similar project in the future, and it's definitely recommended that if in the future similar projects are conducted, it should definitely be considered that some form of flexibility should be introduced to the network. That was my master's thesis presentation. Thank you very much for watching.